See this problem. A small disk A slides down with initial velocity 0 from top of the smooth hill of height h, having a horizontal portion. What must be the height of horizontal portion h to ensure the maximum distance h? Oh, there is some mistake. To ensure the maximum distance s covered by the disk, what it is equal to? What it is equal to? So your disk is here, right? It's smooth. It is smooth. There is no dissipative forces. You have only conservative force, that is gravitational force. So your disk is here. I slice down to this portion and then comes out of this. Then it is getting, it moves like this and falls over here. So when it comes over here, what is the velocity? V. Its velocity is 0 over here. So what's the mechanical energy possessed by it over here? Whenever the mechanical energy possessed will be only P, because K is 0. It is at rest over here. So what is the potential energy, gravitational potential energy at this point? Whenever you calculate the gravitational potential energy, you take a reference base. At this height, the gravitational P is 0. So with this reference, the gravitational P over here is mgh, right? And K is 0. So that's your mechanical energy. And the mechanical energy at this point is the gravitational P plus K. And since there is no dissipative forces, these mechanical energy must be equal. It will only happen that a part of mechanical energy, a part of potential energy has got converted into K. So your mgh will be equal to mg small h half mv square. So this becomes 2g v square. Mm will cancel out. So that becomes v equals to 2g h minus h, 2g capital H minus small h, right? So that's the velocity. That's the velocity over here. And with this velocity, it will move. This is the horizontal velocity. It is not going to change. So what time? There is no vertical velocity over here. This is a horizontal portion. So what is the time taken to cover this height? What is time taken by the body to fall at this point? So that will be given by half gt square, and that is t equals to 2h by g. This is a time taken by this disk to fall height h, right? So that is equal to s equals to vt, that is 2g into, so that is equal to gg will cancel out, and this becomes, right? That is your s. That is your s. Now they are asking what must be the height h of the horizontal section so that s is maximum. We have to maximize this s. In that case, we can just differentiate this part. It is d by dh of hh minus h square. Just differentiate, just maximize this part. So that is, so you are getting h equal to h by 2, right? D by dh is h minus dh. And in fact, when you are taking the double derivative, it's minus 2. It will give you maxima. So h equal to capital H by 2 will give you the maxima, right? Double derivative is coming out to be negative. So S max is going to be h by 2. So that comes to be h. That comes to be capital H. S max is capital H. Okay. So that's how you can do this problem. This is a very simple problem on law of conservation of energy. Law of conservation of energy. Now let's go for the next question. See this question. A small body A starts sliding from height h. This is height h. It starts sliding from height h down the groove, passing into a half circle. This is half circle of radius h by 2, right? Find the velocity of the body at the highest point of trajectory. Find the velocity of the body at the highest point of trajectory. And I must write after breaking off from the groove. See, when this particle is moving from along this path, let's suppose the particle is here, your small body is here. What's the free body diagram? Let's see. So mg, normal reaction n, because the motion of body is constrained in this direction, and then mv square h by 2. H by 2 is the radius. H by 2 is the radius. Say I'll call it r for the time being. R is h by 2. See, in this case, it is in radial equilibrium. It is in radial equilibrium. Suppose, so this is, oh, or better I should draw like, it will be a long radius. So n will be in this direction. Suppose we have theta over here. So in this case, this is going to be theta. So the body is in radial equilibrium. When it is in contact, it is in radial equilibrium. So it becomes mg sine theta equals to mv square by r, right? Now you can see over here, n is mv square by r, mg sine theta. See, as the body moves in this direction, this quantity is falling because k will fall. There is an increase in p, so k is falling, and this quantity is rising. This quantity is rising, right? So a time will come then this will become equal to this. Initially this is high, theta is 0. When you have over here theta is 0, you have the velocity, but slowly this quantity is going to fall, this quantity is going to rise. So a time will come when they will become equal and your n will reduce to 0. So n is falling, this quantity is falling, this is rising, so n is also falling. So a time will come when n will fall to 0. And what will happen at that time? What is n? N is the contact force between this body and the groove. Contact force between the body and the groove. So what does it mean? What do I physically signify when I say n is 0? N is 0 means this body loses the contact with the groove. N is 0 means this body loses the contact with the groove. That is what it means. Now can you tell me the value of theta at which this body is going to lose the contact with the groove? We can find it. For that we have to find mv square over here, and we can use conservation law of conservation of energy. See, there is no friction, so energy in the beginning was mgh, and that is equal to mg h by 2. What is the potential energy over here? This is going to be h by 2, and this is h by 2 sine theta plus half mv square, right? So if I put it this side, this is mg h by 2 minus h by 2 sine theta, that is mv square. mm will cancel out, so v becomes gh 1 minus sine theta under root, right? So if I put it here, the value of n, for n to be 0, your mv square by r must be equal to mg sin theta, right? Must be equal to mg sin theta. So it comes out to be m and m will cancel out. So gh 1 minus sin theta h by 2 g sin theta, this will cancel out, and this becomes 2 1 minus sin theta equals to sin theta, or sin theta is 2 by 3. So the value of theta at which it is going to leave the groove is sin inverse 2 by 3, right? It's going to leave the groove at this point. It's going to leave the groove at this point, and after that it's going to follow this trajectory. I'll tell you, it's going to move like this. It's going to move in a projectile, right? And this velocity, when it leaves the groove, the velocity of projection, I say velocity of projection, will be equal to, I can put it over here, gh 1 minus 2 by 3, that is gh by 3. This velocity is going to be gh by 3, right? This theta is going to be this theta. Okay, so when it reaches the highest point of trajectory, the velocity won't be having any vertical component. Velocity will have only horizontal component, and horizontal component is not changing over here. When it leaves the groove, the horizontal component won't change. There is no force acting horizontally, so horizontal component will remain constant. So what's the horizontal component of when at the time of projection? The horizontal component at the time of projection was v sin theta. So that's going to be horizontal, v horizontal. So this is gh by 3 into 1 by 3. So that is horizontal component. That is horizontal component 1 by 3 gh by 3, right? 1 by 3 gh by 3. This horizontal component at the highest point of trajectory, the particle is going to have only this velocity, right? Particle is going to have this velocity only, 1 by 3 under gh by 3. This is the velocity at the highest point of trajectory. Getting a point? So this is again a problem on law of conservation of energy. In fact, see, you won't be getting a separate question on law of conservation of energy or momentum. Basically, these two laws are very much applied in collision. These two laws are very much applied in collision, right? So we'll see the chapter of collision and see there what are how these conservation laws will get applied, and we'll get the velocities after collision, right? So we'll discuss the next topic we are going to discuss is collision, and there we will be making use of these two laws, right? You won't be getting a separate question on conservation laws, law of conservation of momentum or energy. The best way to check the understanding of these laws is in collision, right? So we'll see the collision in next lecture. Okay, thank you very much.